This is the second video in the Chemistry Key Skills series of tutorial videos. This second video will focus on the periodic table. It will also look at electron configuration as well as isotopes. In this tutorial video, we will look at how the periodic table is organised, including how it came to be in its current state. We will use the periodic table to predict information, including electron configuration. And then finally, we will look at how to calculate relative abundance of isotopes, as well as what an isotope is, as well as looking at the relative atomic mass of different atoms. The big question in this tutorial video is to look at aluminium, where it sits within the periodic table, as well as what we can assume about its properties, its electron configuration, and how it is similar to other elements. So what is the periodic table? Well, the periodic table contains all of the elements that we currently know about. There are 118 elements on the full periodic table. Within your exams, you will be provided with a periodic table and you will be expected to be able to use it to find out information about the elements. The periodic table that you are provided with in your exams is not as complicated as the one on the screen. For example, you will not be given any of the lanthanoids or actinoids at the bottom of the periodic table. So where do these ideas about the periodic table come from? Well, scientists like to see where there are similarities and where there are differences between different substances or different elements. So Dmitri Mendeleev in 1869 started to work on his version of what would then become the periodic table. This was completed in 1871. Mendeleev started to put similar elements into what he called groups, very similar to what we do today. If we look at his group 1, we can see lithium, sodium, potassium, rubidium, and cesium, just as they are today. Within these groups, the elements were also organised into their atomic mass. Some of them do end up in the wrong group, based solely on the fact that he was working with isotopes, so some of the atomic mass numbers were not fully correct. This is something we will look at later on in this tutorial video. Wherever this happened, he switched the order of the elements in order to keep the properties the same. In order to keep elements with similar properties together, he had to leave spaces. These were elements that weren't previously discovered. These gaps have subsequently been filled in, and the elements that fill in these gaps match very closely the chemical and physical properties of the elements that Mendeleev suggested. For example, ecosilicon, which was an element he predicted, is now known as germanium and fits his description perfectly. He also had no idea of the noble gases, group 8. As such, these do not appear within his periodic table. The modern periodic table, however, is slightly different to Mendeleev's because once we'd found protons and electrons, we were able to work out the atomic number. The modern periodic table is arranged in terms of atomic number and not atomic mass. This is a copy of the periodic table that you will receive in the Edexcel exams. As we mentioned earlier, the lanthanoids and actinoids have been removed, as have elements 112 to 118. As we can see, the elements are arranged in atomic number order, starting with hydrogen, which is 1, helium 2, lithium 3, beryllium 4, and onwards. Elements with similar chemical properties are found in groups. These are the numbers across the top, from group 1 to group 0 or group 8. Group 1 is this column here, group 2, group 3, and so on. The group number tells us the number of electrons in the outermost shell of each of the atoms. For example, group 1 would have 1 electron in its outermost shell, whereas group 7 would have 7 electrons in its outermost shell. Group 0 or group 8 are the exception to this, where from neon downwards they all have 8 electrons in their outer shell, as opposed to helium, which has 2. However, all of these have what is known as a full outer shell. The rows of the periodic table are known as periods, with hydrogen and helium being in period 1, lithium, beryllium, etc. being in period 2, and so on. The number of periods tells us the number of shells that each atom has. We can also use the periodic table to let us know whether an element is a metal or non-metal. This involves the drawing of a line onto the periodic table. This is a staircase that fits down from boron downwards, as so. We draw alongside boron and follow our staircase down. This gives us metals on the left-hand side of the periodic table and non-metals on the right-hand side of the periodic table. The elements around that staircase are known as metalloids, as in certain situations they are able to act as either metals or non-metals. Finally, the big block of elements in the middle which do not have group numbers are known as the transition metals. We will look at these further in the separate science or triple science tutorial videos. As we mentioned when looking at the periodic table, electrons occupy shells around the nucleus. The number of electrons within each shell is known as electron configuration. This always follows the same rules. So these shells, or energy levels, can only fit a certain number of electrons in each. And the lowest energy level, or the innermost shell, is always filled first. Within the first shell, you can only have 2 electrons. From the second shell onwards, you can then have 8 electrons, as you can in the third shell as well. You only, for GCSE, need to be able to do the electron configuration up to calcium, which would be 2, 8, 8, 2, as it has 20 electrons. To work out your total number of electrons, you will be looking at the atomic number. Remembering back to video 1, where the atomic number, which was the number of protons, was also the number of electrons in the atom. Using this simple 2882 rule, you can then easily work out the number of electrons within each shell. I want you to practice this by working out the electron configurations for hydrogen, which is atomic number 1, beryllium, atomic number 4, fluorine, atomic number 9, phosphorus, atomic number 15, and potassium, atomic number 19. The electron configuration for hydrogen would just be 1. For beryllium, you would have 2, 2, 2 in the first shell, then 2 in the second. Fluorine, 2, 7. Phosphorus, 2, 8, 5. And finally, potassium, 2, 8, 8, 1. You can also work these out by looking at the period and group that the element is in. For example, phosphorus is in group 5, so it has 5 electrons in its outer shell. It's also in period 3, and it has 3 shells in total. As I mentioned earlier, one of the problems Mendeleev had is that he was working with some isotopes. Isotopes are simply different forms of the same element. This means that they have the same number of protons and therefore the same atomic number, but they do not have the same number of neutrons. This gives them a different mass number. For example, with carbon-12 and carbon-14. where carbon-12 has 6 protons and 6 neutrons, whereas carbon-14 has 6 protons and 8 neutrons. Almost all elements have multiple forms and multiple different isotopes. Some of these can be radioactive, as we will look at in physics. Another 3 popular isotopes are those for hydrogen, where we have hydrogen-1, which is our standard hydrogen, which is protium, hydrogen-2, which is deuterium, and hydrogen-3, tritium. The difference between these is the addition of the neutrons. As we know from the periodic table, all elements have 2 numbers associated with them. The smaller one being the atomic number, the number of protons. The other number is the atomic mass, the number of protons and neutrons. However, we can expand this out further to look at the relative atomic mass. The relative atomic mass of an element is the average mass of one atom of that element to 1/12 of the mass of the atom of carbon-12. So carbon-12 is our reference point for this. By working out relative atomic masses, this takes into account the number of isotopes as well as how much of those isotopes we have, their relative abundance. This is why not all of the elements on the periodic table have a whole number for their mass number. For example, chlorine, which shows as 35.5 on the periodic table. Obviously, we can't have 0.5 because you can't have half of a proton or a neutron, so this is an average of the relative abundance of its 2 isotopes, which are chlorine-35 and chlorine-37. As this number is closer to chlorine-35 than 37, we can infer that chlorine-35 is a more common isotope than chlorine-37. When you are asked to work out a relative atomic mass, this may be written as AR in the question. As we just looked at, different isotopes can occur in different levels of abundance, so they can be more or less common. In order to calculate the relative atomic mass, we can use these relative abundances. To work it out, we need to find the average mass of all of its atoms. To do this, we multiply the relative atomic mass of each isotope by each isotope's relative abundance. We can then add up the results. In order to then calculate the relative atomic mass, we divide this by the total number of all of the abundances. As these are usually given to you in form of percentages, you will be dividing by 100. We will now practice this by looking at chlorine. So as we previously mentioned, chlorine has 2 isotopes, chlorine-35 and chlorine-37. Chlorine-35 has an abundance of 75.76%, whereas chlorine-37 is 24.24%. Our first step is to multiply the relative atomic mass of each isotope by the relative abundance of that isotope. So we would do 35 times 75.76 and 37 times 24.24. This gives us a value of 3,548.48. We then need to divide this by the sum of the abundances. As we were given percentages, the overall number will be 100. So we will do 3,548.48 divided by 100. This gives us an overall relative atomic mass of 35.48 to 2 decimal places. It is important when doing relative atomic mass calculations that you work it out fully and do not just write the answer from the periodic table. We can see that 35.48 is very close to the 35.5 found on the periodic table. However, you must show all of your working in order to get the full marks. In this tutorial, we have looked at how the periodic table is organised, including the work by Mendeleev. We have used the periodic table to predict information, including electron configuration, and we've looked at how to calculate relative abundances of isotopes, as well as the relative atomic mass of different atoms. I now want you to have a go at the big question. So look at where aluminium sits within the periodic table. What would be the properties of it? What would its electronic configuration be? And what other elements may it be similar to in its properties? As aluminium is in group 3, it would have 3 electrons in its outer shell. It would also have 3 shells as it sits in period 3. This would mean that its electron configuration would be 2, 8, 3. It will be similar to the other elements in group 3, for example, boron. It is also a metal, as it is found on the left-hand side of the periodic table. This would mean that it would act like a metal, it would be shiny, it would be able to conduct electricity and heat, and it would be ductile and malleable. In the next video in this series, which will be the third video in the Chemistry Key Skills series, we will be looking at bonding. This will include the formation of ions, ionic bonding, covalent bonding, and metallic bonding. We will also look at the giant covalent structures.